Broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, my name is Lee Pucker. I'm the CEO of the Wireless Innovation Forum, and I'd like to welcome you all to the 22nd in our webinar series. Today's webinar is entitled Strategies for Deploying RFSoC Technology for SIGINT, DRFM, and Radar Applications. I'll do a few brief announcements at the beginning, and then I'll turn it over to our speaker who will go into the details of the webinar. So to start, the slides presented during the webinar are going to be available. They're actually in the handouts right now, but the version that's in the handouts is there's an error in it. So we'll be making available a revised version of the slides later today, and when you'll get a link to those sent to you. We're recording the webinar, and so if you want to review it again later, it'll be available on the forum's YouTube channel. And again, when you get to thank you for attending today, there will be a link to that in there. And if you have any questions about anything that's being presented today or anything associated with the webinar, feel free to email me, lee.pucker@wirelessinnovation.org. A little bit about the interface you're going to be using. I'm assuming everybody's connected to microphone and speakers or telephone for dial-in. You can minimize the interface that you're using so that you can get it out of the way of seeing the slides by just using the little orange button there. We'll do questions at the end, and so if you have questions, type them as you go throughout into the question screen, and then at the end of the session, then I will answer the question. I will ask the questions to our speaker, and he can answer them live during the webinar. And finally, with that, I'd like to turn it over to today's speaker. Our speaker today is Roger Hosking. He's the Vice President and co-founder of Pentec. A little bit of an introduction. Oh, my notes went away. Roger, I'll ask you to introduce yourself then. So I'll turn it over to Roger. Thank you.
Okay, thanks, Lee, for the introduction. And I'm going to light off my presentation now. So let me just make sure that works. Okay. Yes, so we've been doing, this is our 32nd year in business, and we've been doing this kind of technology, that is coupling high frequency signals, typically radio signals, to FPGA or DSP functions for doing digital signal processing, otherwise known as software radio or software defined radio, for a long, long time. And I'm one of the founders of Pentec and have been with the company since the beginning, and have seen a whole range of different technologies being applied to this basic area of the market. And I have to say that the RFSoC technology we're going to be looking at today has generated more interest than any other product that we've introduced over the last 30 years. It's a very intense interest from a lot of different segments of the software radio market, both military and defense, as well as the commercial markets. So quite a wide range of interest, and I hope you'll find the presentation interesting today. We're going to cover several different topics. First, for those of you who are not familiar, I'm going to introduce the RFSoC itself, which is a product of Xilinx, and show some of the unique advantages that it has and why it's so important. And then we'll take a look at some of the market segments. And then for people who want to build products, what are some of the design challenges for taking this very powerful chip and making it work in a real product? And then we'll introduce our approach to how we go to market with this to make it easy for our customers to take advantage of the RFSoC product in a modular form, and how to migrate the function to different platforms, different form factors. And finally, we'll wind up with what are the development strategies for the FPGA and the ARM software before we sign off with a summary. So first of all, as you probably, many of you know, in February of 2017, Xilinx made the announcement of the RFSoC chip, an integrated RF class analog with RF data converters, and basically they claimed it, and rightfully so, as a disruptive integration and architectural breakthrough for 5G wireless and RF class analog technology. So that was the announcement, and what's inside the RFSoC chip itself is a lot of different resources. It's an amazing collection. So first of all, it starts off with the 16 nanometer Kintex UltraScale Plus technology for the logic cells, the DSP engines, the block RAM, and so forth. And then added to that are the advanced I/O functions, DSP engines. You have internal block RAM, internal ultra RAM, which is an enhanced memory, controllers for external DDR4 memories, a PCI Express Gen 4 interface, and then some very fast gigabit serial links that support the 100 gigabit Ethernet MAC that's built right into the chip itself. So it's extremely well supported in terms of infrastructure for a lot of different applications out there. But that's not all. They've also, of course, added the A to Ds and D to As directly into the FPGA fabric on the same chip. And these are not just, modest devices. They are, in fact, on the A to D side, 12-bit 4 gigahertz A to D converters with digital down converters, and then the DAX are 14 bits, 6.4 gigahertz, again with integrated digital up converters. They are connected directly into the fabric with low latency parallel interfaces. But that's not all. Also on chip, on board, is a complete ARM-based processor system with all of the processor I/O signals that are typical to, for example, a processor controller for a real-time system. Inside the processor system section includes a quad-core ARM Cortex A53, a dual-core Cortex R5, a memory controller, a system controller, security manager, platform management unit, and a lot of connectivity so that the chip can be connected to the outside world using USB and SATA and PCI Express and gigabit Ethernet for connectivity to the outside world. So all of these resources are on the chip, and the FPGA fabric itself has direct connections to DDR4 memories, 100 gigabit Ethernet, the GPIO for parallel, and GTY for the serial, gigabit serial links. So what you've got is a complete subsystem on a single monolithic chip, 8 inputs, 8 outputs for RF, and everything that we've just talked about. So as you will probably agree, it's quite a remarkable achievement that Xilinx has presented for our use. So let's talk just quickly about latency, which is quite important to many different applications. And I think most of you know what it is, but basically it's a delay, and the delay not only within an element like an A to D converter, but between the elements. And so these delays can be a critical limiting factor, now more so in the links between than in the devices themselves. Now, why is that? Well, traditionally, devices like A to Ds were connected to FPGAs with parallel LVDS lines. And the nice thing about that method is that it's very simple and it's very low latency, but it has some limitations. It's limited in speed, and it also causes many lines to be required on the PCB, especially as the A to D converters get faster and faster and get into the gigabit range. Those LVDS lines have to be demultiplexed, and so it winds up adding a lot of PC traces and a lot of connections and a lot of pins on the FPGA that are consumed for that parallel method of connection. So to solve those limitations, a new serial standard, not that new, it's been out for many years, is the JESD 204B. And here, what we're doing is converting the parallel connection into a very high-speed serial gigabit connection, often called JESD or JESD 204B. The advantages are that the JESD can handle high-speed A to Ds, and it requires fewer lines to route on the PCB and fewer pin connections to the devices. The problems are, though, that it does introduce latency. That serialization requires a protocol, and it also requires an engine on both the transmit and the receive side to implement. So it's a much more complex interface. Once it's working, it works fine, but often it takes quite a bit of work to get it going. So what the RFSoC does is it really takes the best of both of these, because what it does is it uses internal parallel data converter interfaces inside the RFSoC chip from the data converters directly into the FPGA fabric. So what you get is the benefit of the simple and low latency of the parallel connection, but you also get the ability to handle high-speed A to Ds. And of course, because everything's internal to the RFSoC chip, there are no lines on the PCB to connect them. So it makes it quite simple. So in fact, the RFSoC eliminates all the cons of both the parallel and the serial connection. It kind of gives you the best of both worlds, and it's quite a nice achievement. So you might ask, well, who cares about latency? And some applications are just not affected by latency at all. For example, if you're doing a recording, you don't really care if there's a little extra latency in the connections. Once the file's recorded, it's done and saved on the drive. But there are a lot of applications, for example, most notably countermeasures, where let's say you're building a radar jammer, which has to receive a signal and then do something to it, then send back another signal that tries to defeat a radar system from detecting your plane, for example. So in this case, the latency is very important. The good news is that regardless of whether or not latency is important to your application, the RFSoC covers all applications for all latency requirements. So let's take a look now at some of the market opportunities that have been identified by Xilinx for the RFSoC chip. Multifunction phased array radar. This is also, for commercial weather and commercial radar networks, but of course also a lot of different military and defense applications are very interested in the radar. EW and countermeasures, again, that's a very key part of the low latency advantage that RFSoC brings to the table. Communications, so you have a lot of channels and you need a lot of, say, high density. So for SATCOM, for military and airborne radios, for monitoring, interception analysis, and SIGINT, and then 5G wireless, where you do need the massive MIMO structures. You need to be able to receive and transmit, and of course with A to Ds and D to As on a single chip. That can greatly simplify some of the hardware involved in the 5G wireless. So how does RFSoC really change the market? Well, first of all, it's quite efficient in terms of space. If you take the components that are within the RFSoC chip itself and compare the discrete implementation of those functions, you'll see that it takes about 50% less size and footprint compared with those discrete devices. It also drops your power by about 30 to 40% because a lot of the power in the interconnections that otherwise would be taken with discrete devices is not required because it's all on the same chip in the RFSoC. And that does lead to cost savings as well. It's just more efficient, fewer parts to purchase and interconnect. They're all in the same monolithic device. And then finally, as we've said, latency is greatly reduced over these discrete solutions, where the A to Ds and D to As that are shown down there to the left would almost always be JESD, because that's the most common way of implementing the gigabit, the gigasample per second data converters that are on the marketplace today. What are some of the challenges in using the RFSoC? As a board level designer, you've got signal integrity issues. You've got 16 analog RF signals, 8 A to Ds, 8 D to As with gigahertz bandwidths. You could have the possibility of picking up spurious signals. You have crosstalk possibility and signal path integrity and matching impedance. So designing a printed circuit board that keeps all of those signals very clean, even though they're right in the midst of a very heavy digital circuitry, is a tough thing to do. And then the signal path integrity for the high-speed gigabit serial links that are at 28 gigabits to support the 100 gigabit Ethernet connections. These require extremely careful printed circuit board layout, maintaining impedance and going through paths like connectors and so forth that can often compromise some of your performance. And then clocking the data converter, sample clocks, clocking the FPGA fabric, and then the gigabit serial links can also be kind of a major design issue and take up a lot of time in terms of doing your board design. And interestingly, the RFSoC chip requires 13 different power supplies, and some of them have to be extremely clean. The analog supplies have to be extremely clean in order to maintain the signal fidelity and dynamic range of the RF signals in and out. And then last, the thermal management. How do you take the heat from the device and dissipate it appropriately? So these are all issues that anyone who's taking the chip and wants to design a board is going to have to address. So what we're trying to present today is an idea of, let's say you love all of the advantages of the RFSoC chip. How do you get from the chip into a deployed product in the shortest path? What are some of the hardware strategies? What are some FPGA design strategies? How do you do software development, FPGA development? And how can you get a running start, say, on your competition, so you can get an RFSoC-based product to market as efficiently and as early as possible compared to your competition? So we have some strategies, and we're going to introduce the big strategy, which is the RFSoC module concept, which we call Quartz XM. Now, this is kind of inspired by traditional modular mezzanine designs that we've been working with for years and years, where you have a main board and then you have a module that attaches to it, like our Jade, Onyx, and Cobalt XMC modules have small daughter cards that have A to Ds and D to As. And FMC is another standard that uses the FMC module to contain A to Ds and D to As. So the practice of using mezzanine cards has been in the industry for many, many decades. It's not new. So inspired by that concept, we said, let's make a small module, a small mezzanine module that contains all of the infrastructure required for the RFSoC chip itself, but is an extremely small form factor that allows you to take advantage of those features of the chip without having to worry about all of the very difficult design challenges in making a board. So this chip is 4 inches by 2.5 inches. It's not a chip, it's a module, and it is an extremely efficient in terms of space and laid out very responsibly. But what really goes into this, the idea is to simplify your design effort to get RFSoC technology into your product. We have connectors that preserve all of the RF signals and the gigabit serial signals as well. One 12-volt input to this module generates all 13 RFSoC power supplies. So it simplifies that power supply generation dramatically. It has flash and DDR4 memories to support both the FPGA fabric as well as the ARM processor that's on board. It maintains all of the constraints and design rules for the printed circuit board for bypassing, filtering, size, line spacing, and so forth. It includes clock management, health monitoring facilities, and it really is a great way for you to get the RFSoC into a very small custom space that would be difficult for you to do without the module. Some of the technical details of the Quartz XM, as we call it. XM stands for Express Module, and Quartz is a kind of our trade name for the product line based on RFSoC. You can see some of the technical details. It's quite a complex 28-layer board with some really advanced fabrication techniques to achieve everything that we needed to make the chip run at its optimum. So if we take a look inside, what's inside the Quartz XM Express module, it really, we've talked about it. We're going to just highlight the pieces of it here. There's a power management, there's clock management, there's 2 banks of DDR4 SDRAM, one for the FPGA and one for the processor. There's flash memory, and then there are connectors, and the ones we're highlighting right now are the RFSoC connectors, which use a very, very good RFSoC multi-pin connector made by Samtec. And we also use very high-speed digital connectors for the clocking, as well as for the other I/O, including the serial connections that go in and out of the board. So it's really quite a very carefully designed combination of different features that give you this complete solution all in a very compact module. So how do you do development for Quartz XM, the module? Well, one of the first and most popular platforms in the embedded space is VPX. And VPX would be a great first platform for taking the Quartz XM into a deployed standard open architecture backplane standard like VPX. So VPX also has a lot of standards that are very appropriate for the RFSoC. For example, it has a very well-defined optical backplane standard called VITA66 that gives you the ability on a 3U VPX module to bring the optical gigabit serial connections out to the backplane and between boards or to another system. We also have connections on the backplane for RF signals with signal bandwidths up to 40 gigahertz using the VITA67, which is a coaxial RF backplane I/O standard. And then VITA65 and VITA65.1 are the open VPX standard. That's really the most popular standard that's now being used for deployed mil-aero systems. There's profiles that support all of these new extensions. There's support for synchronization, radio backplane clocks, reference clocks, and it's a really great environment to deploy these high-performance digital signal processing products for the embedded market. So what we did, we created a carrier for the Quartz XM in a 3U VPX form factor. This is called a 5950. So here is the 3U VPX board. We install a RFSoC Quartz XM module on it, and now it's an open architecture board compliant with Open VPX. It has all of the backplane connections according to the VPX standard. It takes advantage of the VITA66-4 optical serial backplane for the 100 gigabit Ethernet links that we provide. It has front panel connections for the RF in, out, and clock. And it gives you a very complete 3U VPX module. It's a complete functional subsystem with everything then compatible with the open architecture standard 3U VPX or Open VPX. Inside, you can see the carrier here is outlined in blue. And this is a picture of it in the upper right. This is the 3U VPX board. And central, outlined in red, is shown in both views, is the Quartz XM module, which then is connected up according to the lines that you see here to the appropriate interfaces on the 3U VPX carrier. We also have a rear transition module, which is part of VPX, that allows you to bring system I/O from the ARM processor to the backplane, the back of the chassis, for connections to things like gigabit Ethernet, USB, DisplayPort, and so forth. And this is a very convenient way for you to get those connections out to the rear panel. We have both air and conduction cooled versions of the 3U VPX product. And for development, we've arranged with a partner to provide a single slot 3U VPX development chassis that allows you to put that 5950 3U VPX Quartz board into that slot, and it gives you all of the cooling, power, power supply, and so forth, the backplane that you need to support it. The front panel goes in on this side in the front, and that includes all of your RFIO, clocks, timing, and so forth. And then the rear panel the rear transition module is on the rear panel, and you can see that supports the ARM processor I/O. And then there's a MTP optical connector that supports the dual 100 gigabit Ethernet. So this gives a very nice, ready-to-run development chassis for doing RFSoC development. So if we take a look at that take a look at the rear transition module. This is a blow-up of it. And for you to do development or connect to other parts of the system, what you can do is connect up in different ways. You can connect up over RS-232. You can connect up over JTAG. You can connect up over gigabit Ethernet. All of these scenarios are valid development connections that support the tools that are provided by Xilinx and by Pentec, the Vivado tools and the Navigator tools from Pentec, which we'll talk about a little bit later. But it's a very, very convenient, ready to use, ready to start development strategy for the RFSoC itself. So let's talk about going to other platforms. We looked at going to the 3U VPX, but the whole idea of the Quartz XM module is that it's capable of migrating to other platforms. So, for example, there is a collection of people who would like to use backplane for the RFIO using that VDA67 standard that we talked about. So instead of coming out through the front panel, what you can do is build a different carrier, a different 3U VPX carrier that brings those analog RF signals instead out to the backplane using the VDA67. You keep the same Quartz XM module, but just have a different mechanical arrangement on the carrier board itself. The nice thing about having all of the RFIO on the backplane is that it really reduces system integration by getting those cables off the front, and saves also in any reliability issues that are associated with the cables on the front. So this is one alternate platform for the Quartz XM. Another is a PCI Express Carrier. This allows you to take the Quartz XM module and plug it right into a PC for a low-cost development platform. This is on our roadmap, will be coming out in the next few months. This is great for doing your software or FPGA development because it's a low-cost platform. And it's also good for continuation engineering and support in case you're deploying a 3U VPX version. You can do a lot of the development and continuation engineering on a low-cost PC. And this also is extremely suitable for benign environments for your deployed system. So if you don't have a military, hazardous, difficult environment that you need to go, but you can tolerate a laboratory environment, this would be great to save money and to have a low-cost platform with the same technology on a PC. But you can also go to other platforms. This is a path, if you want, of how that could be done. You could start with the standard 3U VPX module, or you could start with the PCI Express, but just to start with one of our standard products, and then develop all the software and IP for your custom form factor application. Then you build a carrier for the Quartz XM module using our Quartz Carrier design package. Now, that includes the pin definition of the module, the design rules, layout guidance. We will review your design. You attach the Quartz XM module, and now you've got the RFSoC in a completely different, unique environment. Perhaps this is a nose cone of some kind of a small aircraft or a UAV. But you keep your the standard product as a development platform for doing the other additional development work or your next project. Other custom RFSoC solutions could include multiple RFSoC Quartz XM modules on a single backplane. And this is extremely attractive to a lot of customers who have an array of antenna elements that are located, let's say, up on a mast or in an aircraft. And the RFSoC modules, the Quartz XM modules, can then have a very short, direct path between the antenna elements and the RFSoC chip itself, which then, with a little RF circuitry in between, can deliver digitized versions and for both receive and transmit functions to the elements of the array, of the antenna array. So this is an extremely attractive solution for a lot of customers. Again, this would be a custom design board using the carrier design guide that we provide as a kind of a cookbook for meeting all the rules to make sure you're successful in developing your custom board. Another idea would be to have a small form factor remote box. This is another product that's on our roadmap. And here what we're doing conceptually is we're starting again with the 3U VPX board, but we're creating a new board. We're modifying it to take off all of the VPX-ness, if you want, of the board. And instead, we're going to install special connectors that would be appropriate for a small remote form factor, remote box. So this then is installed in a suitable enclosure, a small form factor enclosure, and it could be mounted, let's say, up on the mast near an antenna. And this then forms a complete 8-channel RF transceiver subsystem, very compact, where you're taking analog RF signals in and out directly to through a short path to an antenna, and connecting down through the mast with cables for power, gigabit Ethernet for control, and then dual 100 gigabit Ethernet to deliver your payload data. That would be digitized data coming in or transmit digitized data going out. So it's a very nice strategy for getting the signal processing and the acquisition a lot closer to the antenna using the small form factor box concept. Now, I mentioned the carrier design package. What it includes all the pin definitions of our module, the Quartz XM module, 3D models, thermal profiles, schematics for our 3U VPX carrier, PCB stack-up recommendations, that is the layering, the design guidelines and routing rules, operating system and bootstrap guidelines for getting started, and then additional guidance from us to review your design. And this does require an NDA because we want our customers to be able to use our Quartz XM module with our product. So what are some of the development strategies for the FPGA IP? Well, it starts off, of course, you're going to require the Xilinx Vivado tool suite, which does support the RFSoC chip itself. It includes IP Integrator, which is a graphical design entry tool that allows you to manipulate IP modules and connect them simply by clicking on inputs and outputs of each module with a mouse, and it will automatically do that connection for you. Those modules are based on AXI4 IP, which standard. This allows you a standardized way to connect easily between modules that come from Xilinx, from Pentec, and from other third parties. So it really simplifies design. You can also use high-level synthesis, generating RTL from C or C++. There's a simulator to verify the design, and there's a tool command language, a scripting language that's part of their tool suite as well. The part that comes from Pentec is called the Navigator FPGA Design Kit, or Navigator FDK, for the RFSoC. What it contains is a complete Vivado project folder that we use to develop the product as we ship it. So you have all the files ready for extending what we give you to your own custom configuration. We also supply a full AXI4 library for all of the IP that we use with source code. So you can choose some functions that might not be in our product from the library and add those to the project, recompile, and get some new functions. We also include resource modules that include DMA controllers, triggering, gating, timing, synchronization, 100 gigabit Ethernet, and kind of very important is we include some reference designs or examples that are very useful as starting examples for your particular application. And since everybody's doing something a little bit different, we decided to start with 4 starter applications that represent what a lot of people, one of which would probably represent what a lot of people would want to do. For example, the first one is a digital RF memory with a programmable delay. Now this would be a great start for someone who's doing electronic countermeasures, for example, where instead of just implementing a delay, you could implement some other signal processing function that could be appropriate for a countermeasure application. Another starter example is just a streaming acquisition engine where the data from the A to D converters is streamed out through a dual 100 gigabit Ethernet. You can get about 25 gigabytes per second of data across those 200 gigabit Ethernet links. So while you probably do some data reduction in the FPGA, getting 25 gigabytes per second of going out or even going back in case you want to use the D2A is an extremely high-speed connection that could be very valuable and faster than most backplane connections currently support, at least through PCI Express. Another, another example is a waveform generator, where people want to generate, let's say, an outgoing radar pulse, and they have a let's say they have a stored table that represents the waveform samples, and that table can come from memory, it can come from PCI Express, it could come across the 100 gigabit Ethernet, or we could even use an onboard chirp generator. This is a frequency sweep generator that's built right in to the example. So this covers a lot of different waveform generation type applications for different types of application spaces. And then lastly, we have kind of a multi-function or multi-mode acquisition to delay memory or to PCI Express or to 100 gigabit Ethernet. This could be used to implement, say, a transient capture in the DDR4 memory. It could be used for acquiring data and processing it at the same time, perhaps doing a recording application and an analysis application in parallel. So that it's kind of a multifunction example that could be useful to some customers. So what we believe is that these starter applications for which we provide full source code and IP can give our customers a good head start on what they're trying to do. far as the software development for the ARM processor, again, Vivado does provide a RFSoC ARM SDK, which includes a complete design environment, integrated design environment, debuggers, compilers, editors, libraries, device drivers, as well as the Xilinx Petalinux operating system for the ARM processor, which also includes Linux tools and utilities. So this is all part of the Vivado offering. And then Pentec's Navigator Board Support Package, or BSP, gives a complete command processor to you. And we implement this as a command processor so that you can send high-level API commands into our board from PCI Express or Ethernet, and we will interpret those commands and execute them. So you can operate the board at a relatively high level. We include a suite of tools, which includes the initialization, control, the ability to control all operational parameters, C language libraries, full C source code, lots of examples, and device drivers for Windows and Linux. Last, we include a signal viewer utility that allows you to view signals that you've acquired, say through the A to D converters, on a virtual spectrum analyzer and oscilloscope for time and frequency domain inspection of the signals that you're acquiring. So as far as the command processor goes, that application, as I mentioned, is running on the ARM processor. And what it allows you to do is to accept high-level commands, let's say across, say, gigabit Ethernet, to the Quartz XM module through, in this case, the VPX backplane and the rear transition module to get a high-level command function implemented. You can also do that same function across PCI Express. So perhaps you have a PCI Express link that goes into across the backplane or is connected through an expansion chassis from a PC. So that again can be used to deliver high-level commands, which we will interpret with the command processor. We offer these flexible options because people have different needs and want to build their systems in a different way. Another nice part about the 3U VPX, the 5950, is that often in a 3U VPX system, you'll have a single board computer that acts as the system controller. And it's often usually the root complex of the system controller. But the Model 5950, our 3U VPX board, can be configured as a root complex. And so it can, if appropriate, let's just go back up here, it can replace the single board computer and save you the slot that the single board computer took and have the 5950 take over its role by virtue of the ARM processor running Linux and running as a root complex. And then the other payload cards that you may have in your system would all be PCI Express endpoints or targets that would be then controlled through the root complex there on the Model 5950. So the whole thing boils down to being able to save the cost and the space and the slot that might otherwise be required if you had to have a separate single board computer in your system. So let's just take a quick summary here. The RFSoC chip itself from Xilinx, as we've seen, offers incredible integration advantages, low latency, all the A to Ds and D to As. What our Quartz XM module does is it simplifies system design. It gives you a small footprint for high density custom applications, and it preserves all of the performance of the device itself using connectors that can be used in a mezzanine fashion. We talked about the Xilinx Vivado tools for both FPGA development and the ARM processor. We talked about Pentec Navigator tools, the FPGA design kit and board support package to do both the ARM processing design development with those libraries and the custom IP development using our libraries and our existing starter modules that we talked about to give you a really good head start. And altogether, this offering and these strategies really help get you to market and get your development done much quicker than if you were to try to design your own product using the RFSoC chip as a starting point instead of the Quartz XM. So that's the end of the presentation. Of course, if you'd like more information, you can visit our website and just go to the RFSoC section, which is very prominent. We have data sheets for the two products that we talked about. We have a white paper. We have Pentech Pipeline. This is our quarterly newsletter. It goes into some strategies for deploying RFSoCs. And then we also have a live signal acquisition video that shows signals being acquired on live hardware that we took this summer, showing you some of the really nice performance that we're getting in terms of signal to noise and dynamic range. So with that, I guess I'll turn it back to Lee. Are you there?
I am. Thank you, Roger, for your presentation. If folks have questions that they'd like to ask, please go ahead and enter them into your questions window. I have the first one to read to you. Roger, how does licensing work for the FDK? Is it one per site?
For the FDK, yes, it's one per developer. So it's like a workstation license, and that can be used for one project or other projects on many projects, but it's a workstation development license. Okay. And there is no runtime licensing at all.
Okay.
In other words, there's no per unit license fee associated with the products that you're developing.
All right. If there's other questions, please, again, everybody, feel free to enter them into the window. I just got a comment that came in that said, "Well done. Do we get college credit for this presentation?" So.
Sure. I'll be glad to send you a diploma. How's that?
All right, there you go.
Thank you for the compliment.
One question I had, I noticed with all those different power supplies coming in, you're running them from a single 12-volt supply. What's the efficiency on your conversion process there?
We're up in the probably 95% range. So I mean, these have been very, very carefully designed to be maximum efficiency. And the fact that we know exactly what the input voltage is and that we know exactly what the output voltage is, you can choose devices that will operate most efficiently at those two known fixed points, as opposed to having a very wide range input voltage support. So we put a lot of work into it, and a lot of that also was done to save the space, because the some of the real estate on this board was very judiciously allocated to certain functions, and we think we've done a pretty good job.
Okay. Next question that's come in: does Pentech support customer embedded designs, albeit smaller form factor than the Pentech Quartz, as beta developments that might leverage portions of the baseline Quartz XM design?
In other words, what you're saying is, could we sell you a development kit that included the Quartz XM and have you use that as a launch pad for doing an even smaller custom design of your own? If I understand it correctly, and I guess we certainly would want to talk to you about that. We want to sell Quartz XM modules, but if we can work out a suitable licensing agreement, if you want to go manufacture something that's derived from the Quartz XM, we would certainly welcome that discussion.
Okay. The next question that came in: what are the AXI4 functions you mentioned? How do they differ from the Xilinx IP?
Okay, we have a lot of our AXI4 library is centric to the signal processing requirements that we have for our customers' applications. For example, clocking synchronization of multiple A to D channels, triggering, gating, delayed triggering. A lot of these things have to do specifically with real-time software radio applications, and not necessarily will be found in any Xilinx collection of libraries. So we have DMA controllers that are extremely well tuned to move data from our module across PCI Express, for example, in a very efficient way. And again, that was carefully designed and developed by us with a suitable FIFO buffering and so forth, so that we can stream data as efficiently as possible for a particular product. And some of our DMA controllers are optimized differently depending on the data rates. The other thing we do is we use these structures in our recorders, where the job one is really getting the maximum recording rate from our modules onto a RAID array. And so a lot of the techniques that we've developed and the IP that we've developed for the recorders and for our board level products are very unique to Pentec. We've got digital up converters, digital down converters with special features, interpolation filters, other kinds of structures in our software radio products that are in the library, and not all of them, of course, are used in any one product, but customers can take our library and choose modules that are there and bring them into the project and recompile to include those modules, those functions as a new design, a new configuration.
Okay. Roger, I've gotten a couple of questions about pricing. I'm not going to bring those up here, but what I can do is forward those to you, and you can perhaps follow up on the pricing questions offline.
Absolutely. We welcome any requests in that nature, of course.
Okay. The next question is, are all analog input signals to the Quartz XM assumed to be at A to D baseband, i.e. FS/2?
We have characterized the A to D inputs in both the first, and which is 0 to FS/2, and in the second Nyquist zone. And we are just finishing up a report showing the performance of the A to D converters in both the first, second, and I believe they're even doing some in the third Nyquist zone. So the answer is the RFSoC is definitely useful in beyond the first Nyquist zone, and we have taken some measurements to show and prove that that's so.
Okay. There's a related question. What is the 1 dB passband cutoff frequency response?
I believe it's above 6 gigahertz, but I'll have to check that. That's a spec I just don't happen to have in the top of my head. We use very wideband balance between the RF connections on the front panel of our 3U VPX module and the Quartz XM module. And the Quartz XM itself uses the Samtec ISO rate connectors, which are rated well above 6 gigahertz. So it depends on whether you're using a 3U VPX board or you're using the Quartz XM module itself. But we've done everything to preserve a very well-controlled impedance path, a very, very high bandwidth by using the best connectors we could find.
Okay. Next question. Any RX to TX latency numbers in the report?
It will be in the report, and this report is just being compiled, but that information is in the report, yes.
Okay. Next question. Are the balance, I'm guessing that word is critical, to getting signals through the backplane?
The signals, okay, I understand. Yeah, in case you're using the VITA67 backplane connections, instead of having the balance then going out to the front panel of our 3U VPX carrier, they would be located in a different physical position so that we would connect up with the coaxial RF inserts that go into the VITA67 backplane housing. And those, again, are also rated for, I believe, at least 10 gigahertz, and some of them can go up to 40 gigahertz in terms of signal bandwidth. So it's a repositioning physically of where the baluns are, but the baluns would be in the signal path between the backplane VITA67 coaxial RF connectors and the Quartz XM module that would be on the 3U VPX carrier.
Okay, thank you. Next question. Does Xilinx have frequency response test data for the Zinc that we can assume for the Quartz XM input response?
I believe we are, if not completely compliant with their specification, at least on the XM module. It might be a little bit less going through the 3U VPX board, but again, we've tried to keep everything capable of meeting Xilinx's spec for the Quartz XM module, so we're not degrading their performance levels in any way that we know of.
Okay. Another question just came in. What are the maximum I/O data rate limits for the Quartz XM VITA66X optical backplane module?
Okay, we did answer that. Well, first of all, the optical links are rated for 28 gigabaud or gigabits per second, and that is implemented in our standard product with 2. Since there will be 8 lanes going out, they're implemented as 200 gigabit Ethernet links, and we have actually measured data payload throughput rates of about 12.5 gigabytes per second for each of those 100 gigabit Ethernet links, which gives you an aggregate of 25 gigabytes per second payload data going across, not raw, but actually payload data. So that's where we are, and that's what we've measured. That's what's working, and it's really working extremely well with extremely nice eye patterns all the way through to the 3U VPX backplane optical VITA66-4.
Okay, that's the last question that we have. So with that, why don't we go ahead and wrap things up? Thanks again, Roger, for the presentation. I know everybody who was attending really appreciated it. Again, for those on the line, we will upload the slides associated with this to the Wireless Innovation Forum's website, the webinar page. You'll be able to get them from there, and we'll also be uploading the recorded version of the webinar to our YouTube channel, so you'll be able to listen in again. Thanks for everyone for attending. Thanks again, Roger, to you, and I will see you all or talk to you all again at the next webinar that we hold.
Thanks, Lee, and thanks for all of you who listened today.